Hey y'all, it's Andrew Couch here, and I just want to say thank you. The channel reached 100 subscribers this week, and I just want to say thank you for all my subscribers and viewers. I plan on continuing this project and making weekly videos on the Tidy Tuesday dataset. However, this week, this Tidy Tuesday dataset is on cocktails, but when I was reading the comments, I noticed a lot of you guys wanted me to make more videos on TidyModels, so I figured it'd be kind of an interesting thing to do some computer vision with the TidyModels package. And with computer vision, kind of like the hello world of like computer vision is the MNIST dataset or database, where essentially it's handwritten digits, where you're trying to classify each image and the number that was written. We're also going to go over some clustering, which is a good way to basically visualize higher dimensional data. So when we open up Markdown, we're going to actually load in the Tidyverse, Keras, and TidyModels. Okay, so what's cool about Keras is Keras actually comes with the MNIST dataset. So that's what we're going to do. We're going to first load it in, and we'll call this the MNIST data. And then in the MNIST data, it actually comes with a train and test set. And within the train and test sets, they have an X and a Y values. So the X is actually the kind of the pixels of the actual image, where it's actually a black and white image. So these will represent, I believe, white, like white, and the numbers will actually represent black, or the actual digit. So we're gonna do this. We're gonna say we're gonna bring in the data set and call it image data. And if we look at our image data, its dimensions, we see that we have 60,000 images, and these images are 28 by 28. So 28 by 28 pixels, which is about, let's see here, 784 total, I guess what we would say features. However, if we look at this, it is a 28 by 28 matrix, but it's a list of matrices. Okay, so what we also have to load in is the actual image labels. So that's what we're gonna do. We're gonna call MNIST data train and then Y. Okay. So when we're actually going to be visualizing these image data sets, these images, or to do the actual clustering, we need to actually convert this into a kind of a digestible format for most of our processing. Okay, so originally this was actually for, I guess, like a neural network. However, what we're going to do is we're going to use the tSNE, or T-Distributed Stochastic Neighbor Embeddings, which is a clustering algorithm. So to do that, we're actually gonna have to reformat this data. So to reformat the data, Keras actually comes with a pretty cool thing where I believe it's called the, where is it? Oops. Where is it? Array reshape. So with array reshape, we give it a X or data. So we'll say image data, and we also give it a dimension. And for our dimension, we want to keep the actual the amount of samples. So in this case, if we'll go back here and do image data and say dim, we still want to keep the 60,000 data sets or images. However, we want to convert these matrices into basically a list of columns, right? So if we do that, we say 28 by 28, it'll convert basically these square matrices into long rows, which is what we want. So we're gonna put this in. Oops, image data. And if we look at the dimensions now, we have 60,000. We still have the 60,000 images. However, this, I guess, square or two-dimensional feature set is now converted to like a tabular form. Okay, and that's basically what we want. Okay, So when doing tSNE, if we actually look at the I guess the creator of the tSNE algorithm, it's called T distributed stochastic neighbor embeddings, and Josh Starner actually has a really good video that kind of explains it. But it's actually a pretty simple algorithm. It essentially just kind of maps these dimensions into a lower dimension and starts and basically implements the similarity by using the t distribution, by using each point's relative distance. So I know I'm not really great at explaining that, but Josh Starner has a really good video on it. And one of the main reasons why we should use tSNE over things like PCA is because tSNE is actually a nonlinear clustering algorithm, and it has many implementations in different languages. So it's a pretty fast and nonlinear clustering algorithm, which is really useful for visualizing a lot of higher dimensional data. Okay, so when we're doing this, since we have 60,000 images, I'm actually going to take only the first 10,000. Okay, so we're going to do that. We're going to take the first 10,000. Oops. Image labels. Oh, wow. Oh, I spelled image labels wrong. That's why. Okay, just that. Labels. Just that. Okay. Image labels. And then we'll do the first 10, 1, 2, 3, 10,000. Okay, so now we have the first 10,000 images. We're actually going to load in the tSNE package, which is called Rtsne. And if we look at the Rtsne package, oops, right, it doesn't have actually a lot of functions. I think it only comes with two functions. So it's a pretty straightforward package. But the main thing we're really going to use is the normalize, Rtsne, the normalize input function. And this essentially centers and scales our data. If we actually look at our image data, the image data, let's see here, max, can we do that? The image data has a max value of 255 and a min value of 0. And that's just kind of like the, I guess, I think like the colors or whatever are in that type of scale. So we need to normalize the input. So we just normalize the input, and that'll see, and that makes basically centers and scales it. So now you see how there's no 255s or anything like that. It's all centered, I guess, like in the -1 and 1 range. Okay. And we're still going to put this into our, we're going to assign that to our image data. And then what we're simply going to do is going to create a tSNE object. In this case, I'm going to call it a tSNE data frame. And we'll use the Rtsne function, give it the image data. And Rtsne has a decent amount of parameters. So if we go here and let's see here, zoom. We can see that there's perplexity, theta, PCA, partial PCA, max iterations, verbose, all this stuff. However, the main thing that we really want to deal with is, I guess, perplexity, right? And what's kind of cool about this is the creator of Rtsne kind of has some nice, like, high level information explaining around it. So what he's saying basically is, loosely speaking, one could say that a larger, denser data set requires a larger perplexity. Typical values for the perplexity range between 5 and 50. And then he also says perplexity can basically be compared to the numbers of nearest neighbors as k. Okay, so what we can do is I'm actually going to set the perplexity to about 25. I think that's a good number because that's basically in between 5 and 50, and we really don't know how we should tune it. Additionally, like if we really wanted to get into Rtsne or just tSNE clustering, we could go and do some type of grid search for the perplexity. Additionally, we can specify the dimensions. So by default, it returns two columns. However, what I'm going to do is we're actually going to ask for 3 columns. Okay, so now we're running the t-SNE algorithm on the 10,000 image data. If you notice, the image data doesn't have the actual labels, so the labels are independent of the actual t-SNE algorithm. Okay, we're gonna create a new chunk, and I thought it'd be interesting when after we finish running the t-SNE algorithm is to visualize the three-dimensional embeddings. And to do that, we're actually going to load in the Plotly package, which contains a lot of cool 3D charting things. So if we look at 3D Plotly plots in R, we can see that it comes with a lot of cool little basic 3D scatter plots. Right? Let's see if it'll load up. And you can see this is just made in R and saved as like an HTML widget. But you can kind of visualize the 3D axes in a pretty intuitive manner. And it's kind of fun to kind of drag around. You can like see the callouts. You can, I think you can zoom in too. Yeah, you can zoom in and stuff like that. So it's a pretty cool package. I kind of want to start using Plotly for my dashboards, but I haven't really gotten into it too much. Okay. So it's still running, perplexity of 25. Okay. What else can we look at? Yeah, there's also a lot of things that you can specify. You can do like PCA too, with the t-SNE, and you can also like run t-SNE over and over on itself. So you can do kind of like this feedback and iterative process on it. Okay. So now that we have the t-SNE data frame, we can kind of look at it. And it's actually not a data frame. It's kind of like a list of these random things. But if we look at the, I guess, Y, you can see that we have our 3 embeddings that we wanted that represents the image data set, which is actually kind of nice because we transformed 784 features into 3 features that can really summarize our entire data set. Okay. So once we load in Plotly, what we're going to create is kind of like a Plotly df. And what we're going to do is we're going to create a as tibble, and we'll do the t-SNE df y, and then we'll say let's see here, we'll do a cbind what is it, the image data, yeah, and do that. So now that if we look at our Plotly, Plotly df, let's see here. Oh, what's it doing right now? Okay, there we go. We have not our image data. We need our image labels. There we go. So now we have our image labels. Let's see here. Okay, so to actually create the plot, we use the Plotly function. We give it our Plotly data. We specify our x, which is x equals to v1, our y, which is equal to v2, and our z, which is equal to v3. When we have to use these tildes, I guess it's like a kind of unique to Plotly. Not really sure why. And then we can also specify our color labels. So in this case, we'll do image labels. And now that I think about it, we probably need to do some processing. For example, our image labels are integers, so we need to mutate that. So we're just going to call it labels. I think it's easier to type. So labels equals image labels as dot factor. Let's see if that works. Okay, so we have that, right? And you're going to get run into this error with, I guess, Markdown. What we're also going to have to do is add the markers, right? And it's still not going to say it's not supported, but we're going to put this into our plot object. So we'll say Plotly, I will say plot, what is it, 3D. Okay, so now that we have our Plotly object, what we're gonna do is we're gonna just save using the HTML widgets and say save widget plot 3D, and the file will equal to t-SNE plot.html. Okay, so it's gonna save that. I'm gonna open up my Tidy Tuesday. Oh, and we find our t-SNE plot right here. And now we can actually visualize our t-SNE plot. Okay. Ooh, maybe I have to make this. I'm actually going to change this because it's not actually putting this as a factor. It's more as a continuous variable. So let me change that. And then mutate labels equals as dot factor labels. Okay, let's see if that changed it. Okay, well, I guess it didn't. well, we can kind of look at something and see that, okay, there appears to be specific clusters, right? And actually makes a decent amount of sense. There's defined clusters, and these clusters are representing the actual numbers, right? And we can see with the color labels. So we can see that it's actually working pretty well. The t-SNE algorithm actually found out some relevant clusters that actually clustered each image to its respective handwritten label, which is pretty great. Okay, so once we have that, what I was thinking about doing is we could probably put this into our TidyModels framework. So since we have our TidyModels package already loaded into, and we have our Plotly DF, right? I'm actually gonna, oh, that's why I just said. I'm gonna say, there we go. Sorry about that. I totally forgot that I was renaming it. Okay, we're gonna actually look at this again just for more clarification. There we go. So now you can definitely see how there are set clusters that are respective to their own labels. And t-SNE didn't even look at the actual labels, right? So there wasn't any data leakage. It just found the clustering of the actual black pen writing and decided that they were very similar things. And intuitively that makes sense. And that's how we kind of look at digits. We say, oh, well, this line looks like a 1. It looks similar to the past ones I've seen. So we're going to put them together. And obviously there's probably going to be some problems, right, with say like, oh, what's the difference between a 7 and a 1, right? Sometimes people make the top of the 7s really short, and you can mistake that for being a 1. So it's not perfect, but it did cluster it pretty well. You can see how some of the clusters do contain the wrong points, and that's fine. We could actually tweak it and do that, but we can see some definable clusters. Cool. So we have our Plotly DF, and I'm actually going to create, I'm going to say select minus image labels, boom, and then I'm going to call this our model data. Okay, so now let's start actually doing the modeling. If you think about it, we actually did some feature engineering. As a common thing to do some type of feature reduction before you start modeling, if we actually look at the MNIST wiki, you can see that there's a nonlinear classifier that they use, and they just used 40 principal components, okay, to achieve like a 3.3% error rate. In this case, we're actually only going to use 3 components from our t-SNE clustering, our t-SNE embeddings, okay? So we're using 3 features to really predict, I guess, 10 labels, which is kind of a big deal. That's actually very impressive, right? So that's what we're going to do. So we have our model data. We should probably make our tidy split. So was it initial split model data, and we'll say prop equals 0.8. Okay, and then we'll create our tidy training, tidy split, tidy testing, tidy split. Okay, so we're gonna say create model data and partition into train and test. Cool. Actually, perform tSNE visualize the embeddings using Plotly. Cool. And then we'll say reformat images to tabular format. That's basically what we did. Okay. Cool. So we created our training test sets. Now we need to make a tidy recipe. And if we notice with our model data, the ranges are not centered, right? They're in different ranges. Yeah, they're probably the same ranges because they're using the same embeddings, but they're not between 0 and 1, or not in the -1 and 1 range, which a lot of models prefer. So in this case, we're gonna actually create a recipe. So create a recipe for pre-processing. Tidy rec, which is our tidy recipe, and we're gonna be predicting our, our labels again? Yeah, labels, data equals our tidy train. Okay. And what we're gonna do is we're gonna step center all predictors, step scale all predictors. Okay, cool. So I was reading more about the tidy recipes, and basically you're always going to do a tidy prep, right? So we're going to say prep, tidy rec, view it, what's it doing? You know, it's doing center and scale for those values. So I've been doing the tidy juice, right? Where it's like tidy juice, juice tidy rec, tidy prep. And what juice really does is it just creates the it creates like the the training, the pre-processed training set. If you wanted to apply it to, say, like another data set that you just left out, you'd actually use the bake function, right? So be bake, and you'd be tidy prep, and then you could do like tidy test, right? And it would apply your recipe to the whatever data set you wanted to do. You could also do tidy train, and we'll do the same thing. So if you really want to apply the recipe, you just do bake, and you give it the prepped recipe and a data set. Okay. Realistically, we don't really need to use these things because I'm just kind of doing the modeling procedure. But if you want to do like a pipeline, stuff like that, these will probably be very necessary. Cool. So I'm just gonna go to the next chunk. Okay. So we're gonna say training models, and for this Tidy Tuesday, I thought it'd be interesting to kind of do, I guess for every time I do a Tidy Models, to basically use a different model. And with computer vision, one of the models that they use that is actually a really intuitive model is a K nearest neighbor algorithm. So if we look at the Tidy Models package, let's see here. Oops. My internet. My internet. So we're going to use the K nearest neighbor package, K nearest neighbor model. And the K-NN model is actually pretty intuitive. It basically is doing kind of what the t-SNE algorithm is doing, where it's basically assigns, where you basically set the amount of neighbors, and neighbors basically represent the amount of points you want to use. And the basic intuition between K-NN is saying that you're basically asking a certain amount of neighbors how they would classify themselves, and then you take the majority of vote. So if you ask, say, 10 neighbors, right? If you go up to 10 neighbors and say, where are we, like what state are we in? And they say, oh, well, 9 out of 10 of them say we're in the state of Iowa. Then you would classify that area as Iowa. And in this case, this area can be basically used as a sample in the data set. Okay, so we're going to create our first workflow. So workflow, add recipe, and we'll do tidy rec. Okay, so we have a recipe. And then we're going to do the tidy K-NN. And we use a nearest neighbor. What is it? The nearest neighbor uses neighbors equals tune set mode classification set engine KKNN, K nearest neighbor. One thing that we should note is that this this problem is actually kind of a harder problem because there are actually 10 labels, which makes it into a multi-class classification a problem. So a lot of times with multi-class classification problems, usually the class balance is not correct and it's highly imbalanced data, or say like 3 out of the 10 classes are very frequent and the remaining 7 out of 10 are very rare. However, in this case, if we actually look at our, say, tidy train and count the labels, we can see that we pretty much have an equal distribution of these labels, which makes the MNIST, or the handwritten data set, a very great toy data set to work with when you're creating models. Okay, so first we're going to say create a K-NN model. We should also always create a baseline model. So we're going to say create a baseline model. Okay, and what we're going to do is we're going to use a logistic regression model. And this is a multinomial regression. I actually tried the logistic regression when trying out multi-class classification. I kept on running into an error, so I think you might have to use a multinomial regression to do multi-class classification that are analogous to a logistic model. So we're gonna tune the penalty. We're gonna also tune our mixture, because all these linear regression or GLM style models come with a penalty and a mixture, I guess. We're going to set the mode to classification, set engine to GLM net. Okay, so we have our baseline and K-NN model. Now what we're going to do is we're going to create a grid search. Create a grid for the models. So we'll set this for the K-NN grid. So we'll call this K-NN grid regular. Give it the parameters, which are neighbors, and we'll give it the length, or the amount of levels. And this is like the amount of parameters we're going to try. In this case, let's just try 10 parameters. If we look at our K-NN grid, we can see this saying 1 through 10. Honestly, I'm not really a fan of this. I actually I would like to actually change it, but it doesn't seem realistic for how many features we have right now. Okay, so again, what we're gonna do now is we're gonna create a baseline grid, and this is the logistic. So logistic grid regular penalty mixture levels equals 10. Okay, so we have our grid, and now what we're going to do is we're going to start training up these models. First, we must make we're going to do this the carrot way. So we're going to basically we're going to give it our grid of parameters and tune a model, but we're actually going to use KFolds cross-validation to actually do the main evaluation for what are the best parameters, or we're basically going to use KFolds to do the parameter search. So we're going to create a KFolds object using the KFold, the vfold CV, give it our training set that we'll train our models on, and we'll say 10-folds. Okay, so create KFolds object or data set. Yeah, and then we're gonna start tuning our models. So we're gonna train our baseline first. So we'll say logistic tune grid, give it our workflow, and add the model to it, which is the TidyLogistic. Then we're gonna give it our resamples, which our resamples is the tidy KFolds. And then we're gonna give it our grid, which our grid is the logistic grid. Additionally, we're gonna create the K-NN tune, give it the same thing basically, tune grid, add model, tidy K-NN, oops, give it the same resamples, tidy KFolds, give it our grid, K-NN grid, and we're gonna run this. I'm sure this will take a while because we're training basically like on 8,000 samples. So I'll get back to you guys once it finishes. Boom. Okay, so the models finished tuning, and now we're gonna actually analyze the training process and see what was actually the best tuning parameters. So first we're gonna grab the logistic tune. So collect metrics, and we look at this. We can see that there's it brings accuracy and ROC. So I'm pretty sure ROC and AOC is not really useful for multi-class classification metrics. I believe there are a multi-class ROC metric. However, I think with TidyModels they only give you the binary. So we're actually gonna filter it out. So filter dot metric is equal to accuracy. Okay, and then we're gonna do select was it penalty, mixture, and then mean, and we'll just ggplot it out. So ggplot as x equals penalty, y equals mixture, color equals mean plus geom point. Okay, so that's not a great way to visualize it, so we're gonna do a different way. Pivot longer minus mean. There you go, and we can do a better ggplot. So y goes facet wrap. Whoa. Oh, that's what, man, I'm losing it. Okay. Value and then mean. There we go. So we can see how the mixture kind of has this weird seesawing effect, right? And then we can also see our penalty as our penalty increases, our actual mean performance or mean accuracy goes down. Cool. Okay, so now let's look at our K-NN metrics. So collect metrics. This should be, let me see what it's called again. Okay, because we only have one parameter that we're tuning, we're gonna just filter out dot metric equals accuracy and then ggplot the neighbors. So as x equals neighbors, y equals mean, geom line. Okay, and we can see that I guess our optimum neighbor is 5 neighbors. Additionally, we can see that our k-nearest neighbor seems to have much better performance than our linear regression or logistic regression model. However, K-NN is definitely prone to overfitting, and honestly, the amount of neighbors we used is definitely suspect. Where the less amount of neighbors, the more likely it is to overfit or the more sensitive to outliers. Okay, and that's kind of makes sense, right? If you ask only one person for the answer of like some problem, it's highly sensitive to that person. So that person could be right or could be wrong. But if you ask, say, 100 people and take the average of it, then you're probably more likely to be right. Okay, cool. So we're gonna create the tidy best. I will say tidy. We're gonna create the new models. Let's say create new models with final parameters. Okay, so tidy logistic, finalize model, tidy logistic, and then logistic tune, select best, and this time we're going for accuracy, and we did that, and then we'll do the tidy K-NN, finalize model, tidy K-NN, Jesus, sorry, and then we'll do K-NN tune, select best, accuracy. Okay, so we now have our two final models, right? Yeah. Boom, and then we have tidy K-NN. So now we have our two optimal models. Cool. 5 penalty of I don't know and 0.6. Okay, so now we're gonna create our final metrics. So use our workflow, add our model. In this case, we're gonna use our tidy logistic, last fit, tidy split, and we'll then collect our metrics. Okay, and we can see our accuracy is 92%. Very good for our model, for our logistic regression model. Now let's evaluate our other one. So tidy K-NN, last fit, tidy split, and then collect metrics. Okay, and we can see something. Our K-NN model definitely does a little bit better than our tidy logistic regression model. However, if you think about it, there's a 3% difference. And this 3% difference is substantial in some use cases, right? However, we got to also acknowledge that a tidy logistic regression formula is going to be a little bit faster, right? You could put this in as probably like a SQL database and run it, assuming that you have the actual tSNE embeddings. With a K-NN, you kind of have to save the actual data set because it has to reference it, right? So it has to say like, okay, since we're using 5 neighbors, we're going to get a new data set, new data point, or new data sample, or new image, and compare it to 5 other images that are similar to it. And you can see how that can add up, especially when you're putting something onto scale. So I think that's about it. This is a pretty quick video, honestly. But we can kind of see how TidyModels is definitely getting more intuitive for me. And I think these videos kind of are solidifying the specific process that you do when creating these models. I'll see you guys next week, and yeah, tidy on.